December 11th, 2025. NASA releases the strongest evidence yet for an atmosphere on a rocky planet beyond our solar system. This discovery challenges everything scientists thought they knew about planets orbiting close to their stars. The planet is TOI 561b, an ultra-hot super-Earth that should not have an atmosphere. Theory predicted it would be stripped bare billions of years ago, but James Webb Space Telescope found something impossible: a thick blanket of gases surrounding a world of molten rock. This is the story of a planet that rewrites the rules. TOI 561b orbits its star in just 10.77 hours, less than half an Earth day. The planet sits 1/40th the distance between Mercury and our Sunday, so close that one side permanently faces the star, tidally locked in eternal daylight. The radius measures 1.4 times Earth, but the density tells a strange story: just 4.3 grams per cubic centimeter. Johanna Teskey from Carnegie Science Earth and Planets Laboratory states, "What really sets this planet apart is its anomalously low density. It is less dense than you would expect if it had an Earth-like composition." Two possibilities emerged. First, exotic interior structure: a small iron core, a mantle made of unusually light rock. This could make sense. The host star is remarkable: 10 billion years old, twice the age of our Sunday. It belongs to a region of the Milky Way called the thick disk. The thick disk contains some of the oldest stars in our galaxy. They formed 8 to 10 billion years ago when the universe was young. These stars are iron-poor but rich in alpha elements like oxygen, magnesium, and silicon. They orbit the galactic center at different angles than younger stars. Their chemistry reflects an earlier epoch of cosmic history. Teskey explains, TOI 561b is distinct among ultra-short period planets in that it orbits a very old iron-poor star in a region of the Milky Way known as the thick disk. It must have formed in a very different chemical environment from the planets in our own solar system. The planet composition could represent worlds that formed when the universe was relatively young, a glimpse into ancient planetary systems. But composition alone could not explain the low density. The team suspected something else: an atmosphere making the planet appear larger than its solid body. But this seemed impossible. Small planets baking in intense stellar radiation should lose their atmospheres. Billions of years of ultraviolet light, X-rays, stellar wind, all stripping volatiles away, atom by atom. Ultra-short period exoplanets were expected to be bare rock, airless, lifeless, just scorched surfaces radiating heat into space. Some previous observations supported this. 55 Cancri E shows signs of a molten surface with minimal atmosphere. Several TRAPPIST-1 planets appear to lack substantial air. Years of telescope observations found atmospheres elusive on small, hot worlds. But TOI 561b demanded closer investigation. Scientists turned to the most powerful infrared observatory ever built, James Webb Space Telescope. In May 2024, Webb pointed its near-infrared spectrograph at the TOI 561 system. The observation ran for 37 continuous hours, nearly 4 complete planetary orbits. This marathon session was part of General Observer's Program 3860. NIRSPEC operates in the 3 to 5 micrometer wavelength range. This near-infrared light reveals thermal emission from hot planets. The instrument splits incoming light into component wavelengths. Each wavelength carries information about temperature and atmospheric composition. The technique is called secondary eclipse photometry. As TOI 561b orbits, it periodically passes behind its star from our viewpoint. During this eclipse, only the starlight reaches Webb. Before and after eclipse, both star and planet contribute light. By measuring how much the combined brightness drops during eclipse, scientists isolate the planet contribution. This reveals the dayside temperature. If the planet is bare rock with no atmosphere, the temperature should reach maximum values. The dayside would glow like heated metal. Predictable physics, simple radiation. Webb measured the brightness drop across multiple wavelengths. The data showed something unexpected. The dayside temperature appeared to be around 3,200 degrees Fahrenheit, 1,800 degrees Celsius. If TOI 561b were bare rock with no atmosphere to redistribute heat, the dayside should reach 4,900 degrees Fahrenheit, 2,700 Celsius, hot enough to vaporize common minerals, hot enough to melt any known rock. But the planet measured 1,700 degrees cooler than expected. Where did the missing heat go? Thank you for being with us. Please subscribe, share, and like. The answer points to atmosphere, a thick, volatile-rich envelope surrounding the planet. Angeli Piet from University of Birmingham analyzed the spectral data. She states, "We really need a thick, volatile-rich atmosphere to explain all the observations. Strong winds would cool the dayside by transporting heat over to the night side. Atmospheric gases do two things. First, they absorb infrared light emitted by the hot surface. Water vapor is particularly effective. Carbon dioxide also absorbs strongly. These molecules trap some radiation before it escapes to space. The telescope detects less light. The planet appears cooler. Second, winds circulate heat. The atmosphere flows from hot dayside to cold nightside. This redistribution prevents the dayside from reaching maximum temperature. Energy spreads across the planet. Without atmosphere, the nightside would be frozen solid. Heat could not flow through solid rock fast enough." Piet continues, "Gases like water vapor would absorb some wavelengths of near-infrared light emitted by the surface before they make it all the way up through the atmosphere. The planet would look colder because the telescope detects less light. It is also possible that there are bright silicate clouds that cool the atmosphere by reflecting starlight. Silicate clouds, clouds made of vaporized rock. At 1,800 degrees Celsius, minerals like forsterite and enstatite can exist as vapor. They might condense into tiny droplets in cooler parts of the atmosphere. These clouds would reflect incoming starlight back to space. Additional cooling. The team considered other explanations. Could the magma ocean itself circulate heat without atmosphere? Partially. Molten rock can flow. Convection cells might form in the liquid surface. But calculations showed this effect too small. Without atmosphere, the night side would solidify. Convection would stop at the day-night boundary. Could a thin layer of rock vapor explain the observations? Vaporized minerals hovering above the surface? Possible. But the observations demanded something substantial: real pressure, real atmosphere. The evidence became clear. TOI 561b possesses a thick atmosphere despite 10 billion years of intense radiation. But a deeper mystery remained. How does this atmosphere survive? Stellar radiation should ionize the upper atmosphere, create a hot corona of escaping atoms. Over millions of years, the entire atmosphere should evaporate into space. Yet here it persists after billions of years. Tim Lichtenberg from University of Groningen proposed the solution. He states, "We think there is an equilibrium between the magma ocean and the atmosphere. At the same time that gases are coming out of the planet to feed the atmosphere, the magma ocean is sucking them back into the interior. The planet's surface is not solid. At 1,800 degrees Celsius, rock melts. Basalt, granite, peridotite. Everything exists as liquid, a global ocean of molten minerals. This magma ocean is not stagnant. It convects. Hot material rises from the interior. Cooler material sinks back down. This circulation brings volatile-rich magma to the surface. Deep in the planet, enormous pressure keeps water and carbon dioxide dissolved in the melt. As this magma rises and pressure decreases, dissolved gases come out of solution. Like opening a carbonated drink, bubbles form, rise, burst at the surface. The degassing releases volatiles into the atmosphere above: water vapor, carbon dioxide, sulfur compounds, silicon monoxide, magnesium oxide, all the gases that can exist at these extreme temperatures. But the process works in reverse too. The atmosphere presses down on the magma ocean surface. 10 bars of pressure, 20 bars, maybe more. Under this pressure, atmospheric gases dissolve back into the liquid rock. Water enters the magma structure. Carbon dioxide reacts with silicate minerals. An equilibrium forms. The atmosphere loses material to space through thermal escape, but the magma ocean continuously replenishes it from below. As long as the interior contains volatiles, the cycle continues. The atmosphere survives. Lichtenberg adds, "This planet must be much, much more volatile-rich than Earth to explain the observations. It is really like a wet lava ball." Wet lava ball. A planet where volatiles exist, not as surface oceans or polar ice, but dissolved in an ocean of molten rock, where the boundary between atmosphere and lithosphere is fluid, where gases cycle between air and magma in continuous exchange. Earth has water in its interior too. Minerals in the mantle contain hydroxyl groups. Ringwoodite can hold significant water, but the total amount is limited, perhaps equivalent to 1 to 5 Earth oceans. Most of Earth water sits on the surface in liquid form. TOI 561b is different. The entire mantle might exist as magma ocean, thousands of kilometers deep, containing perhaps dozens of Earth-ocean masses worth of water, all dissolved, all available for exchange with the atmosphere. This massive reservoir can sustain atmospheric pressure despite constant loss to space. The discovery has profound implications. It challenges the hypothesis that highly irradiated exoplanets lose their atmospheres completely. The research paper, published in the astrophysical journal Letters, states, "These results reject the popular hypothesis of complete atmospheric desiccation for highly irradiated exoplanets and support predictions that planetary-scale magma oceans can retain substantial reservoirs of volatiles." This opens a new field of study: geophysical investigation of ultra-hot super-Earths through atmospheric observations. The atmosphere becomes a window into the interior. Its composition reveals what volatiles the planet contains. Temperature patterns map wind circulation and cloud formation. Spectral features indicate the depth and chemistry of the magma ocean below. The research team is now analyzing the complete data set, mapping temperatures around the entire planet, searching for specific molecular signatures in the infrared spectrum. The goal is to identify exactly which gases compose this atmosphere. Early candidates include water vapor and carbon dioxide. Both are volatile. Both dissolve readily in magma. Both absorb infrared radiation strongly. Silicon monoxide is possible at these temperatures. Magnesium oxide, even vaporized iron. The team will also look for variations in temperature and composition across the planet. Does the night side cool enough for gases to condense? Do mineral clouds form at the terminator between day and night? Does the atmosphere collapse on the night side, raining condensed rock back to the surface? Future observations will use other Webb instruments. MIRI operates at longer wavelengths, 7 to 12 micrometers. This range is sensitive to carbon dioxide and other molecules. It can probe cooler layers of the atmosphere, build a three-dimensional picture of atmospheric structure. Ground-based telescopes will contribute. The upcoming extremely large telescope in Chile has a 39-meter mirror. Its high-resolution spectrographs can detect individual absorption lines, measure precise chemical abundances, track atmospheric winds through Doppler shifts. Other ultra-short period planets will be observed. Is TOI 561b unique? Or do other lava worlds host similar atmospheres? Finding more examples would reveal whether magma ocean atmospheres are common or rare. The planet-thick disk origin might be crucial. Perhaps only planets that formed in volatile-rich, low-metallicity environments can maintain these atmospheres. Ancient stars, old stellar populations, different chemistry than the solar neighborhood. Each discovery expands our understanding of planetary diversity. Hot Jupiters, mini-Neptunes, super-Earths, sub-Neptunes, ice giants, lava worlds. Each class challenges assumptions based on our solar system. Each reveals that nature builds planets in more ways than we imagined. TOI 561b represents a new category: magma ocean planets with thick, volatile atmospheres. Worlds that blur the line between rocky planets and gas envelopes. Objects that maintain atmospheric pressure through continuous replenishment from molten interiors. The universe constructs planets we never predicted. Atmospheres persist where theory said they could not. Magma oceans sustain volatile cycles over billions of years. Ancient stars host complex planetary systems, and we are only beginning to understand the full diversity of worlds beyond our solar system. Thank you for being with us. Please subscribe, share, and like.